like to introduce Basavaraj, Soppannavar. He comes from Toshiba, from the Irvine office in SoCal. He's a senior data strategist, and he's got his master's from UCI. He's here to talk about purpose-built NoSQL databases in IoT.
Good afternoon. Thank you, Angelina, and thank you all for coming. So I work for Toshiba, and Toshiba has built its own NoSQL database product called GridDB. It's a highly scalable, distributed NoSQL database. And today I'll be talking over, first half will be a little bit of generic introduction of what IoT and what IoT data looks like, and about IoT databases. So this is what my agenda looks like today. I'll be talking about Internet of Things, a couple of slides, then IoT data and what their properties looks like, and this GridDB, it's the NoSQL database product, and the real use cases where GridDB has been used. So IoT, people talk about the predictions, 50 billion devices, 20 billion devices by 2020, whatnot. So these are the number of connected devices on the left side. Then the IoT economics is about like what's the revenue projections of Internet of Things applications or technologies. So that's around $500 billion, I would say. So Gartner projects around $300 billion. So most of the data you see, or most of the revenues you see, they don't come from your phones or wearables or something like that. But if you see, 70% of all the Internet of Things revenue comes from either business and manufacturing or healthcare. So these two account for 70% of IoT revenues. So this is what a technology stack of IoT looks like. So you have devices at the bottom, you have applications or users at the top, and you have all these intermediate layers like connectivity. You have Wi-Fi, Bluetooth, or you can use mid-range, low-power connectivity as well. Then you have data aggregation. Then you do sort of analytics on top of that data. You store data. You do visualization analytics. You apply machine learning algorithms on top of it. So on all these cases, security and privacy and device and data management are pretty common. So this is what the whole IoT stack looks like. And the right side is some of the examples, what I was talking on the left side. So this is what Toshiba's full stack for Internet of Things and big data looks like. So we have so many different things. We have point of sales, all the devices on the left hand side. So it's like flipped around 90 degrees. So you have devices sending data, then there is data or data ingestion component. Then you have event bus, you have data distribution service. Like most companies have their own service-oriented architecture. People are transforming to newer technologies. So this is the Toshiba's IoT stack. Today I'll be talking about just one part of it, which is the NoSQL database software called GridDB, and it's been phenomenal since it's been used since 2013. So it has been internal since it was developed in 2011, and Toshiba has been using this internally for their own customers for the IoT solutions. So Toshiba built solution across GridDB along with different components. So recently, Toshiba open sourced GridDB, which is just a small portion of the entire IoT platform. So just taking a step back and see what IoT data and what are the requirements of these IoT databases look like. So you see, since you are in a big data conference, you see a lot of data. You see structured data, unstructured data. You see data coming from all types of resources. But there are some unique properties of IoT data. So the unique properties, I'll give you just example of some devices. Let's say your home smart meter, it has 3 different sensors, and it's collecting data every 30 seconds, I would say. So this example has every 30 seconds. So you have voltage, current, and temperature. If you see a single record, it is less than 100 bytes. But if you see, if you gather, aggregate all these data together, you end up getting millions of records, probably billions of records over months of time. So I have a couple of examples on smart meter data that has been used or deployed already. I'll go through it. So what are the properties of IoT data? So mainly IoT data you deal here is not about video, a single data record which is like in terms of gigabytes, but we are talking about very small record size data, but the volume is larger. So you get n into small number of data where n is really, really large. The second is people talk about structured, unstructured and whatnot. Most of the IoT data, because devices are manufactured to perform a particular task and they do it all the time the same way. So most of the IoT data captured here we talk about is mainly structured. Then there is quite amount of periodicity. It might be, it might not be. Some events might be sporadic. So I would say I would put periodicity as one of the properties of IoT data. So and finally, this is the most important factor, is the timestamp. So most of the IoT data is associated with the timestamp. Even your tracker, Fitbit tracker, or Apple Watch, all the data that is sent to your phone or whatever app you are using, it's all timestamped. So these are some of the properties of IoT data. So to handle this kind of data, what type of database do you need? Or if you have a database, what kind of operations or what kind of data that the database should handle? So it has to be highly fault tolerant and highly available, because you don't want to miss a single point if it's a mission critical application. Second, it has to do really well in terms of read and write performance. So if you have billions of records and if you just click on something and want to get a report which takes 5 minutes, it doesn't make any sense. So read and write performance, because you're dealing with large volumes of data, data ingestion matters a lot. So write performance is also a big issue. So the database should also deal with time series data. So when I say time series data, you don't have to do time series operations by themselves. Application developers don't have to do that. But if the database provides those kind of functionality, that would be a really good use case. Then fast search and range queries are a few. For most of the data in motion, we talk about IoT in motion. So spatial and geolocation support is must needed attribute. Then we have real-time streaming support. We are no longer dealing with data at rest, but we are dealing with data in motion as well. So if you're not doing analytics on a batch data, most of the data you're talking about here is streaming data. So all these are fine, but you can simply make use of the regular existing database if your data is not increasing. So here I'm talking about scale out functionalities. Most of the traditional SQL databases, they don't scale out, they scale up. So if your data keeps increasing, you have to go back to your boss, say, hey, my data is increasing, I have to replace my old legacy server. Now I have to bring in a new server or a database server. But here we talk about the distributed concept, which is the scale out concept of database systems. So this is what the evolution of database management looked like, DBMS systems looked like. Earlier we had, in the 90s, just the regular RDBMS. Then we moved to OLAPs, and people realized, hey, we want some database for the operational reasons, and we want some database for analytical reasons, so that I can go back and look at the data. Currently we have RDBMS, Hadoop, OLAP, all whatnot. Then there is a new breed called NoSQL databases. So we see a lot of smart companies like Cassandra, or smart databases like Cassandra, MongoDB, which are like document store, column store, then there is key value stores, then there are graph stores. So all these guys have different data models, the way they scale out, the way they write data to the database, those differ. But NoSQL DBs are mainly scale out databases. So that brings me to our database product called GridDB. It's a purpose-built, it's in-memory. I didn't talk about in-memory versus pure in-memory versus hybrid versus just on disk. So it's an in-memory NoSQL database mainly for IoT use cases. I wouldn't recommend. So you have all the Swiss knife kind of databases where you can perform most type of operations, but they're not specialized in one of those. But this is different. This is mainly for IoT use cases. I wouldn't use GridDB for banking transaction purposes. So it's a highly scalable, in-memory distributed IoT database. And it's open sourced recently. The code is available on GitHub if you guys want to try it out. So this is what if I combine GridDB and the first slide I showed about the IoT stack, where you have devices at the bottom, you have applications using at the top. This is how our most of our use cases look like. So these are all the real use cases. The EPS is like the electric power system systems software that has been used in one of the electric power companies, and that the photovoltaics, what do you say, the solar farm also uses data from the actual solar cells, which is in turn stored in GridDB and is used by the application user. Then we have building energy management system, home energy management system. I'll go into a little bit of details in the next few slides. So these are all the real use cases that was built. So it's so like I told, the data model for RDBMS, as you all know, is a relational base, table structured. Then you have NoSQL databases with wide column stores, document stores, simple key value stores. The GridDB has something called as key container data model, where it's a simple key, but the value is not a simple value. It's a RDB type of a table. So that's the key differentiator here. So it has its own advantages, and this is how it looks like. So you don't know how your data needs are going to be like for the next 1 or 2 years. So you start small, you keep adding nodes as you grow, and so to read data from that data store, you use SQL for the RDBMS, but we have something called as TQL. It's also a query language very similar to SQL, to query GridDB. So you keep adding nodes as you grow. So these are the NoSQL data models I was talking about. You have a simple key value store. You have examples at the bottom, column-oriented store, the way how you store data. Then you have document-oriented model, where it's key and the document may be JSON or BSON, which is a binary object. And then key container. That's what GridDB table looks like. So here, GridDB has key container. Container is, like I told, you can visualize it as a RDB table, and the schema is fixed. So that's one thing which is very similar to the SQL product. So more details on key container data model. So it comes with a schema, so you guys have to decide the schema beforehand. It supports 2 types of schema. So you're dealing with time series data, then you want to store metadata. So use time series data for, let's say, the sensor of this room, like it senses temperature and it senses every 10 seconds. So you have timestamp associated with it, and the sensor sends data every 10 seconds, or 10 seconds. So you use time series container for it. That's how it looks like on the right hand side on green. Then the collection container is like, hey, I want to aggregate all the sensors from this whole building. I have like 20 of those. I have the sensor ID, the name of the sensor, and the specification. Let's say room number is ZHS159, and that's the sensor name. So why do we have this type of model, or what does it provide? Why do you have this kind of model? So ACID is one of the main the topic the RDBMS or database management systems talk about. ACID stands for atomicity, consistency, isolation, and duration. So most NoSQL databases give up on ACID properties because they are scale up. So here, with this type of key container data, this model, we can restore ACID compliance. So that's the main advantage. And since it has a fixed schema, your queries will be really, really fast. And the final one is again like, how do you query data? So you use SQL language, which is just very subset of SQL. So just give you an example, I'll stick to the smart meter. So these are all your neighbors. Let's say you're staying in house number 1. So this is how you model. So each smart meter sends out data whatever time is allotted for it periodically, and it senses voltage, current, and temperature. So this is written in Java. You just define a static class, which is like you define a schema. Hey, SM data is like smart meter data is like a structure in C, and I have timestamp associated with it, and these are the 3 readings I'll be reading it. So you create a time series container, and once you create a time series container with say name, which is a key, which is SM101, 101 is like house number 101, and then this is the bottom line is how you create a container, and then as you keep on getting data, you just insert data to this container. So you create containers for various houses or various sensors. So talking about 3 main properties of GridDB is like high performance, scalability, and reliability. So performance, I stress here is because it's a hybrid composition. It's both in memory as well as it uses disk. What I mean is, so you have a 4-node cluster, you have 4 different servers running GridDB, and you have memories from various machines. Most of your data resides in memory. So there are some pure in-memory databases. There are limitations to it. Let's something like, hey, your database size cannot be more than the memory size, which I don't want to do. So GridDB is inherently hybrid, saying that it works mostly like a cache. So most recently used or most recently accessed data stores in memory. So your queries would be really, really fast in terms of 100 to 200. I have the slides next. So these are the performance results. We have benchmarking results from something called Yahoo Cloud Servicing Benchmark. This is a pretty famous benchmark most NoSQL databases use to compare against their competition. So Cassandra was supposed to be the fastest among other famous NoSQL databases. So we ran this. There's a white paper on the website if you want to see what the configuration details were. So it was an apples to apple comparison. So GridDB performed like 400 to 500% more than Cassandra, and the latency, if you see on the right hand side top, was so less. So this is mainly because GridDB utilizes memory efficiently. I have a graph next which will show you how it differs. So it's not about high performance. You might be having a high performing database, but what if your system is not stable? So let's talk about stability. So we did a stability test, the same kind of workload. By the way, these are the workloads A, B, C, D, F are Yahoo Cloud Services benchmark workload. Like workload A is like 50% read, 50% write. B is like 95% read, 5% write. C is more updates than writes. So, so this presentation is shared. I have slides at the end if you want to go through what YCSP is in more detail. So we did a stability test for 24 hours to see how these two systems perform. So YCSP performed, or say GridDB performed quietly reliable. I mean, the performance did not deteriorate after 24 hours. So that's the red line is from Cassandra. So the reason why we have so much variation is those clients, YCSP clients, benchmark clients, those are all evenly distributed. So the clients don't know where the data is residing, whether it's residing in memory or onto the disk. If it goes on in memory, the throughput was really high. If it goes on disk, if the data was reading or queried from the disk, it was a little less. That's why we have a lot of variation. So moving on, we have high availability. So how GridDB achieves high availability is pretty two types most people or most distributed systems perform is you have master slave on one hand, you have peer-to-peer on the other hand. So we have something called as advanced master slave to avoid single point of failure. And there is a common concept of split brain in distributed systems. It's not happening here because we have a few standard forum policies applied. And we have something called as autonomous data distribution. So if you have a 5-node cluster, if you have a 20-node cluster, you don't really have, the clients don't really have to know where their data is residing. Let's say your replication factor is 2 or 3, so if one node goes down, your data is still retained because it's replicated across nodes. And when I say a data distribution table, all you need is a cluster address, and which is the master node address. The client writes it to the main cluster, and the data is distributed across all the nodes. So load balancing is taken care of. So the reason why we call this as IoT database is because of first 3 features about performance, reliability, and stability. But this is the main differentiating factor. We have a lot of time series operations or functions that we provide for application developers, such as like expiry release function, where say, hey, I'm sensing this sensor data for 3 months, which is of no use, and I want to save on my IT costs. So I just say, let this data expire after 360 days or 720 days. So that can be done. Second, on time series data, you can have aggregation functions. So you can have normal aggregation functions with a set of integers, but when it comes to like time series data, let's say, hey, give me the average temperature of this room from last month to this month. So those things come pretty handy, just like standard deviation, variation, and all other calculations. Then some more advanced features like sampling and interpolation. Let's say this sensor sends data every 10 seconds, but I am not interested in that as long as it's working. Let's say I want to get, hey, what's the temperature of this room start of every hour? So give me that. So you can sample the data. So those functions are provided. Say you have one missing data. Let's say there was some issue with your connectivity, with your Wi-Fi goes down, and you miss 1 or 2 data points. So you have interpolation functions where you can interpolate, assuming the data is spread even. Then of course you have trigger functions for notifications. So let's switch gears and see what type of real use cases, the IoT use cases, where we have seen GridDB being deployed. The first one is building energy management system. I have a little bit details on this. And the second one is smart meters again, and smart city. So BEMS, so Kawasaki Japan, the BEMS company manages more than 100 buildings. So they deal with more than 1 petabyte of data, sensor data each year. So we are talking about a lot of data here. So, but from a single sensor for an entire year, you just gather 2 gigabytes of data. I'm not sure whether they store this data, 1 petabyte of data, for the whole year, or they just throw it off. So we're talking about like 5 MB of data every day per sensor, which averages to 2 gigabyte of data. And depending on the size of the building they are managing, it can be about 100 to 2,000 sensors. So they switched from the old system to the GridDB system because they could see they could add servers, they could take out servers because of the scalability. Simple data model. Data model, as I showed you previously, it was so simple. And the third one is time series operations. Their BI tools, they could do a really fast they throw out fast outputs for their visualization and BI tools. Second is the smart meters for the electric power company. This is one of the top, the 9 top electric power companies in Japan. One of them started using GridDB since 2016 April. I have more details on the next slide. So they had traditional RDBMS, so they saw a significant increase in throughput, more than 2,000 times. Their overall processing cost went down, their CIO was happy, and their data center costs were reduced. So this is the example of how they're doing it right now. So currently it's in production. There are more than 3 million smart meters that are sending data to this electric power company. data size is not so much, it's around 3 terabytes. But if you see, the record size of each data is just 200 bytes. And we have 13 billion records. So processing this 13 billion records, even though the data size is not so big, used to take 1 or 2 days, maybe more. But now, this is how their system looks like. They have different clusters for different operations, but for the same data. So they have something called as balancing, which is they call imbalance. So there are power generators, power distributors. So they estimate the demand of what it is. So finally, the calculation for all this 2.6 terabyte of data was completed on a 3-node cluster, and MapReduce jobs were run on top of it. So that was about smart meters. This is a smart city project. There is a city called Ishinomaki City in Japan. So they were hit bad in the 2011 tsunami, so they had to start it off again. So they have something called as community energy management system, under which comes so many other systems like home energy, building energy, and few others. So GridDB has been installed in most of these systems, and they wanted to use it for long-term retention because GridDB has its own storage engine where you can persist data, and for high-speed processing, of course. So POC, we recently did a proof of concept for another electric power company with the same type of data. And here we were dealing with around 9 terabytes of data with 43 billion records. And this is the actual execution time. It says around 96 minutes for the entire month's power calculation, charge calculation, sorry. So what are the additions, languages, and connectors of GridDB? So we have 2 editions. Earlier we had only one, which is commercial version. Now we have both the community version, which is open source, and we have a standard edition. There are a few features that are, most of the 99% of the features are supported in the open source, except for the few ones like online backups. Let's say you want to scale out, you want to increase, or you want to take one server down. So you need to stop the whole cluster in community edition to and make it rerun again. But in this commercial version, you can do it on the fly. So again, for AWS users, GridDB is available on AWS if you have instances on it, both the standard as well as community edition. And these are some of the connectors because database cannot work on their own. We have so many interfaces for languages, Java, C, C++, REST APIs, and Ruby. A few others coming down the line, depending on what customers ask. MapReduce, again, since it's a database dealing with data at rest, you need to run MapReduce jobs for if you have a Hadoop cluster running, you can do this. We have KairosDB. KairosDB is another time series database. Most of our customers, most users, they use KairosDB for just the time series part. So if your application is bound to time series or KairosDB, then we have KairosDB connector as well. And of course Spark, and there is a new blog on as to how to connect Kafka cluster to GridDB as well. And these are some of the feature snapshot of GridDB. Again, hybrid composition of in-memory and disk is one of the main reasons why we have great performance. And ideally, we have tested the horizontal scalability up to, theoretically, you can scale up to 1,000 nodes. We have tested it up to 100 nodes, but depending on your use cases, do you want to make a single large cluster or you want to make small 10-node clusters and multiple clusters, depending on what architecture your organization is using. And yeah, we have ACID transactions guaranteed at the container level, TQL for querying language, and that's most of it. And these are some of the useful links. That's our developers website for most of technical articles, papers, white papers, and blogs. You have, so I really like the technical reference and the API reference if you really want to get started. Then Quick Start Guide is the one. And that's my contact. And that's pretty much it. Do you have any questions? Thank you. Yeah.
Why did you choose